feel free to use the chat during the talk. I'll try and collate questions and then come back to you in roughly the order that you posted them, so that we can ask Daniel that. Okay, so we have today Daniel Angelov from Efemarai, who's going to talk to us about extending the industrial machine learning ops pipeline with the needs for robustness and continual improvement. Yeah, so I'll just, without any more ado, I'll hand over to Daniel. Yeah.
Perfect. Hello, everyone. It's nice to talk, and hopefully we'll get a bit of a discussion going on afterwards. So happy for that to happen. And in the meantime, let me just share the screen, and we can kick it off. So I assume everything is going as expected. Okay.
Yes, everything's fine.
Great. So I wanted to kind of give a bit of insight into how we can think about the MLOps space, which is the process of deploying these ML systems into the real world, a bit from an industrial perspective, and how we can think about this intersection of robustness, thinking about security, safety, and with the needs of actually the deployment of the system into the real world. So, an idealized way to think about what's going on right now is that we have the problem that we are trying to solve. We can collect some data. Best case scenario, we clean and label it. So to figure out what we need to do, based on that, we can create a specific model to target the data that we have. We can train it, and as a result, get kind of an idealized idea about like what's going on and what's the target of and how well we are performing. But that's not really what's going on, and it shouldn't really be the case. And there are a few more steps in what I call the modern pipeline that have been created to kind of aid and address some of the challenges that are happening with this process. And even though the main part of the pipeline still remains the same, there are a few more steps that you can see around validating the output that the model is having, which is, I think, something that this node in particular is generally very interested in, trying to figure out kind of this intersection between the way that industry is thinking about these processes and the way that the developer community need to also create tools to support this easier. And of course, there is another process that is completely targeted at deploying these models. And then the question there is about scalability. How do we make sure that there is uptime? And obviously, as we're dealing with real world data, it is extremely important to think about monitoring of those deployed models. Make sure that we are processing the data in the required fashion, and actually that we are not incurring edge cases due to these as the system is running and as the data in itself in the real world is also changing. It's kind of very important to make sure that these things are going on. And of course, as the tracking of the performance of the system goes, the circle comes back to, again, collecting some part of this data that we've seen in the real world, cleaning and labeling and iterating. And this kind of loop of continuous improvement is something that is quite well established. And one of the nodes that I kind of already highlighted is it's really interesting to think about what exactly is the current status of conforming how these systems perform versus what we think needs to happen. And when we think about this process, it's not really necessarily only about the developers' tools themselves, but also about how does this validation output that is used by the developers to improve the models, how can that be audited and viewed from either a regulatory body or an external provider or even the end user to verify that the systems they themselves are consuming is up to par to what they have expected in the first place. And I guess the way that we believe about this in Efemarai is really that any critical system, any safety critical system in the cyber physical space obviously needs to go alongside formal specifications of what is the domain in which the system works, what is the expected input and output relationships, and kind of this is a prerequisite to development of the machine learning model itself. And the extra kind of information and how we see this validation is really in what we say as robustness testing. And this is kind of the process of how we think that we need to explore the full set of specifications and the operational domain that they define, and in order to create this domain coverage diagram, let's call it this way. And obviously this is much better defined than what is the current process that is purely thinking about static test sets that very quickly become outdated. And as a byprocess of the way that we do this investigation of the operational domain, we also find novel failure cases that the ML algorithm itself is misperforming or misbehaving in a particular way. And we can kind of think about what is the out of domain operations in these settings. And obviously this is very crucial and important data because it allows us to identify what are the type of failure cases, how does the performance degrade, and where should we address our next kind of iteration loop of the system itself. And when I'm talking about testing, I think this is kind of a very good diagram, and just let me read it for you. I have an ongoing fear that all my unit tests pass, but they are meaningless. So whenever we think about the current way that we test ML systems, we do it with static data set that really mimic what the software engineering world has seen 10 years ago with the introduction of unit tests. But since then, really, we have seen dramatic improvement in how what is a more advanced strategies of trying to make sure that the large pieces of software infrastructure that we currently use are actually robust and they work within how they're expected. And one of these modern strategies is property-based testing. And the way that it works, it really requires three things. The first one is to describe the input or the domain or operational domain where we expect the data to come from. And just to ground this talk a bit more, let's imagine that we're dealing with a computer vision model that is targeted at recognizing some properties or finding particular objects. And so we can think about it in a settings that, these are natural images. We can talk about time of day or lighting or any other sort of perturbation that you can think about. And the second step is really to describe what are the unchanging properties of this domain, or what is the expected behavior. For this computer vision system, it can be the fact that the label shouldn't change, or the uncertainty should scale with the size of the object that we're trying to detect. Or if we think about any form of tabular data, it can be about the gradient of the slope of the change of the output. And this is kind of something that is can be defined for the purpose of the exact test that we are performing. And I guess the final case and what we need is really for the computer to try and search for these edge cases that degrade the performance of the system. And of course, there are multiple ways of how these things are structured, but in reality, it's about making sure that the operational domain is well covered and we can provide some form of understanding about the areas of good performance and sub-performance. And
Daniel, can I interrupt with a question?
Yeah.
Sorry, it's just I was wondering if the properties that you're expressing, are they probabilistic properties? Is it a particular logic that you follow? What sort of properties are you able to express?
Right. I think it really is right now a bit agnostic to the exact properties. So you can think about them. Right now, they're in a state of on a case, so on a sample basis. So we are thinking about the properties on a particular instance of the world. So basically a sample from the domain. But of course, actually, this is an interesting conversation about a group of points where we can think about distributions and how those changes. But you know, after I guess in the third step, when we think about edge cases, it really is a byproduct of the search process that we perform. Is that usually we get clusters of samples, and we can then analyze and perform either some form of causal analysis or causal strands of the different kind of changes that are done in the domain that lead to these failure cases. Does that make sense?
I'll let you go again. Move on. I'm not fully clear how the properties are expressed, but I think that might be
okay. I have further on some examples, and hopefully those will clear things up. Right, and the idea about robustness testing is really not new. Like for people that work in the systems engineering domain, you know, control this type of evaluation is really something that is fairly standard, and making sure that the domain of stability is fairly well known, and this is kind of a physical property that can be evaluated. And really, it's not a matter of running simple, you know, one-off test. It's about whole system performance evaluation. And I guess another way to ground a bit more what we think about the operational domain is when we speak about images, it's very hard to say, you know, actually our domain is all the possible variations of images. This is fairly untractable. But what we can try to compress this set of domains is to this operational domain, which would allow us to measure particular properties in it that we are interested in. And we are trying to make sure that our system is robust to these perturbations in this property. So overarchingly, what we can do is we can take the standard data sets that any industry can use. We can measure these properties. We can perform our search in this operational domain, which allows us to do this evaluation much more tractably, and then later on evaluate the system within the data domain that it is expecting it by synthesizing the image backwards in its original data space. And to clear things up even more, let's take an example. We have on the lower left an image. We have, you know, we can see that there is a deer, there are some trees in the background, and it's semi-dark, so it looks as if it's dawn. So we can then take this this vector in the operational domain and say, oh, actually, let's see how the system is performing if it's you know, in different variations of evening. So we can now change this aspect of the domain, resynthesize the image, and now we can evaluate the performance in this case as well. Or maybe we want to change the background from some trees to a highway if we're evaluating it for some interstate problem. And we can basically change very particular properties that we are measuring in a way that is realistic for the system to observe during its operation, rather than analyzing you know, pixel-based or very concrete, minuscule changes that are more associated with random perturbations rather than observations that are expected in the real world. And so we can go through an example, but it really what this system allows us to do is to couple the data set that people already have, the model that they're already training, and with these specifications and properties that we are interested in, and really generate an understanding about how well this system performs in these different acts as a variation, and maybe it is going to imply to the user or to a body about where should the model be improved or the data set be improved. And it kind of gives a lot more information about the processes that can be taken rather than tracking the current scores or like data set slices or confusion matrices, which don't necessarily give much insight into which part of the data set, for instance, needs to be explored. And one of the public use cases that we can share is with this traffic sign classification. So here we can kind of talk a bit more about the properties as well. So we have this, the system that takes in an image and has to infer the class of the traffic sign that we get. So it's either a stop, a yield sign, turn left, and so on and so forth. So the properties that we want to maintain here is that regardless of the domain and where we are in this domain, the property of the class that is the stop sign or a yield sign should not change. So basically, and the operational domain that we can think about here is either some pixel noise or small occlusion. So you can think about tree branches, stickers, or regardless of what size the sign is or what perspective it's viewed, the property needs to remain the same. This is kind of the prediction should not really change. And just to make it a bit more visual, what you're going to see, the operational domains are color-coded. We've expanded with a few other types of variation that we may expect to degrade the performance. And now we have created this, the operational domains and the dimensions on which we evaluate the system. And so we can take in a sample from the data set that we obtain, and we can actually try to figure out to move it around actively within the domain and try to actively find cases where the system misbehaves and underperforms. And this allows us to quickly create kind of areas of performance where we expect the system to behave well and where it does not. And so, running this on in our case, what we obtain is that so the gray bar, you can see it says 98%. This is the original performance on the data set. If we create different types of variation of the data, we can see that actually, for instance, the system is quite susceptible to occlusions, which is at 3 o'clock on the dial, so 63%. And we can see that actually the system is not behaving well when it has different branches or things in front of it. So this is kind of informing us about, even though the original performance is quite high, this does not translate to what users may be seeing as the performance of the system in the real world. And just to kind of show that we work also with different use cases, so different object detections and semantic segmentations. They're interesting cases that we can talk about. And for instance, we can start, talking about false positives and false negatives. So here we can evaluate how robust is the system to the detection of this plane. In this case, we can see that there are areas where if the plane was coming from this direction, it would have been correctly identified, or maybe we can create different false positives, which are really something that's also treated very differently in the systems, just because it governs a reaction from the system. So these are multiple ways that we can, tune in the system to the different kind of specificities of the domain with which we are working in. And so now that we have basically run through the system, we have seen these failure cases, we have identified them. Not only have we reported this back to the users as to what they can improve, but also this is now a very critical and valuable asset that can be used. So this data set of unseen failure data can be used in multiple different stages. And I guess the first and most obvious one is actually to add it back to the training set and repeat this process of model training and specification and testing. And an interesting aspect is that this is before what we got before the addition of the data. And after we add the data, we can see that the original accuracy may have increased by a single %, so this gray bar, but our robustness to occlusions has improved dramatically. So this is what we can identify, that this type of data that we generated is actually quite important to make sure that the system performs much better in the overall domain that we are evaluating it at. And another use of this data is actually, in reality, what happens is now we have a data set of particular cases where your model is actually misbehaving. And so this allows us to then try to create another set of detectors that when the system is running in real time in the wild, it can identify similar input cases that are very close to the data. We know that the model misbehaves. And so we can flag this data for either for the fact that the model should not be confident in this prediction, because from our testing, we have identified that this is an area where it should not be trusted. So a different type of uncertainty evaluation, or this data can be flagged and actually sent off to the labeling team such that we can map this unseen synthetic data set to some real data that has the same properties that are going to improve the model in itself. And so if we apply this to our original use case, and for this case, the extra images that you see are from a completely different data set. It has nothing to do with what the model has been trained on. But you can see that for cases where the model has not been accurate because of different contrast shifts, we can see that the stop sign has been really faded away and has mimicked what we see it, or maybe it's in a very strong contrast with the background. So, either a dark stop sign on a white background, or, another type of variability. And for occlusions, you can see that we have correctly identified some cases with tree branches or stickers in front of them. Or even this fading away can be thought of a sort of occlusion. So this is really a useful tool to bring back useful pieces of data back to your data set and make sure that the system is continuously improving basically as it's in the wild. And the way that we really think about it is that we're focused from a developer's perspective. We believe that the easier it is to use, the more likely people to make the right decision. But also what we are trying to kind of source and trying to figure out is the right way to really think about the output and the forms in which it is useful, not only for the developers community, but also for either the end user or for extra other bodies that are overlooking the performance of this model in itself. And I guess there are a few kind of open questions that I've highlighted just to spark the conversation, and I really hope we can go there. It's, from an academic perspective, is how do we, convey the level of how much we trust the system, based more than just these slices of these data sets or these uncertainties. And it's also, to the different stakeholders, that is from the developers to the end users or to someone overseeing it. And of course, a bit more concrete and research-based, it's about, looking into uncertainty and propagation of, and detecting this kind of domain shift within the system. And of course, so far we are really working in operational domains that are fairly easy to enumerate. It's actually a very surprising that there is a large number of these cases where even such a very decent amount of variability can be very accurately annotated. And for people that are, I guess, from an industrial perspective or the partners, it really is the case that these type of systems are quite easy to to run and to evaluate what their current performance is. And so it would be quite interesting to collaborate and figure out how we can perform some form of comparison in the different cases that these folks are using. And of course, feel free to email me with any other questions. Yeah, so thank you.
Okay, so thanks, Daniel. We should all show our appreciation and do a bit of clapping probably now. There we are. We have a couple of questions coming up immediately. I've got a few as well, but I dare say that the others will come, but we'll take them in order. So I think can you put your slides back up and maybe scroll back to the aircraft example, you know, the one, because I think Ajitha's question is relevant to that. So Ajitha, do you want to come in and ask your question?
Either the aircraft example or the traffic sign example. So I think I'm just trying to, because you use the term property-based testing, which I think I've understood very differently, and maybe it's used differently in academic research as opposed to how you're using it. But in property-based testing, what you typically do is you define a property that you want the system to hold, or your function, program, model, whatever it is. And then you give it the preconditions, so the assumptions in your environment. And then you say, does this property hold? And in your case, in the traffic sign, the slide that you have here, or in the aircraft detection example, what is the property? What are your preconditions? Because you did mention you want to get from the operational domain, you want to get what assumptions are there or what conditions are there. But I didn't see in your presentation any example of a property or environmental assumptions.
Okay, so I guess the way that we think about this is that as input to the system, it really is the sample that we're looking at, which in this case, it's the image, or well, either the image of the stop sign or of the general of the field. And the property that needs to hold is that the label should remain unchanged. And here, this is just one of the simplest properties, but for the aircraft detection, additional properties may come about for instance, the tightness of the bounding box. So for instance, or so the smaller the object, the more, for instance, leeway we can give for the bounding box to be around that object. If it's closed, we can assume that it should be quite tight. So this is kind of performance constraints. And of course, we can have additional quantities of just uncertainty of like model uncertainty as outputs. So these are kind of like the properties that we can fix.
Okay, so you are really focusing on instance level properties rather than system level or model level properties.
Can you give me an example? Maybe I'm just
I can share my screen. So if you just Google property-based testing, the tool that most people use is called Quick Check. I'm trying to share my screen, but I don't think am I not allowed to, Stuart?
Hang on. Let me just check. Can I make you? I think. Hang on, Ajitha. Yeah, I'll just check. I think Suzanne can make you into
okay. If it's too much hassle, let me just copy paste. That's fine. So I'll copy paste in the chat window. Oops, this looks absolutely awful, but okay. So here, this property, even though it's highlighted in a very funny way, for all ABC strings, the concatenation of A, B, and C always contains B, is an example property that's given, where it says that, look, for any input A, B, and C that satisfies strings, which is the precondition, the program needs to guarantee that B will always be a substring of the concatenation.
I guess in our case, it is that for every image and label pair, regardless of the type of augmentation we perform, the label should always remain the same.
Okay.
I guess, yeah.
All right.
Or, yeah.
I know Philippa has a question, but maybe I can ask something. Daniel, can you go back to the deer example?
Okay. Let's do this. Right.
So here you have these things like dawn deer trees. Do you see those as properties of the example?
I guess this is part of the vector space in which the operational domain exists.
And then you use this as a way of varying in the operational domain.
Yeah. And
so
this is obviously a very high level depiction of the actual properties. They're a bit more fine grained, but I think it gives the
I think the problem is these variations may not hold. Sorry?
Sorry, Ajitha, on you go.
No, I just meant these variations that you're doing, contrast, all this occlusion, it may not even be relevant to the domain you're testing, and it's not necessary the label should hold. So these are very general. This is similar to what Philippa pointed out. It's a very general sort of transformation across images in several domains.
Of course.
It's domain specific.
Yes, and I think this is the operational domain of, I think it is something that is defined on a use case per use case basis. I think as in reality is the case that, not all the transformations are, can be transferred to another domain, but I think there is a large subset that is useful on which, folks can start building up their own domains.
So perhaps now, Philippa, do you want to come in and follow up on this discussion?
Hi, yes. I was quite particularly interested in the operational domain sort of sets of things you had. The wheel you had, the big circle, looked very much like a set of sort of camera failures more than a set of things that you might just happen to come across in the operational domain. So your examples, with sort of contrast, shift, and so on, seemed very much sensor failures, whereas your examples at the beginning, the ones you were just discussing, were actually sort of variations that would naturally happen and should have been considered in your original, perhaps, data set as variations of input that you would just naturally come across. And I mean, the problem with this is coming up with some sort of systematic way of finding them. And I was wondering whether you'd looked at any methods for this, whether you used your wheel as a starting point normally, or where they came from, really.
I think you're kind of touching a very interesting point, which is something that, this is a long-term research thread, is to how to identify this axis of variations automatically. I think there are, special cases for this operational domains that we can automatically identify. As you can see, like the first, third are indeed associated with camera failures. I think the next third is more geometric perspective changes, and the final third is associated with the perceptual, the visual appearance of these objects. So indeed, this is just an example operational domain. I think for cases that are similar to the aircraft, tracking, there we can have a much broader definition of how should the outlook of the aircraft, look like. What is the location? There is an operational domain, some weather conditions that we can add, and so it really is an extension to the type of changes that we can perform. And obviously this is an initial subset. We're building it up, and this is, I guess, kind of a call also to both the research perspective of like what are sensible operations that we can perform, that we can evaluate, that carry the most type of alignment between what is the augmentation that's being performed and the observation in the real world that happens. And also from an industrial perspective, what are the type of changes that they basically see their systems failing at, and so this is something that we can start tracking and basically add to the wheel and build up the domain this way.
I mean, and these examples are very image specific because that's the example you've chosen. But I imagine, say you were doing, I don't know, some sort of sound machine learning system, you would have a very different set of changes that could impact on your failures on output.
Yeah, that is the case. This is, I think, the broader picture here is that what we are presenting is a horizontal platform, and obviously the domain dimensions are based on vertical. So currently, like I presented some for vision, we have another set that is based for language, and another set for voice data, or for cybersecurity. Even this is something that we have been approached. So there is the domains and the verticals are obviously something that we're building up constantly. But I think the takeaway is really that thinking about the continuous improvement and the robustness should be a factor of the expected variations that we want to see in the world, and to make sure that we are tracking them individually and seeing how the model is how is it a success, how basically susceptible it is to different types of variations.
Okay, I think Alex has been sitting very patiently with her hand up for a long time, and so maybe if we pass over to Alex and get her question. I think, Philippa, there's still, this one's going to run and run, I think, so we'll probably come back to you.
Hi, Daniel. Thanks for your lovely talk. So the examples you gave, the challenges involved sort of recognizing a positive example when it was kind of a very crappy, not very clear positive example. But I'm wondering about negative examples. In other words, things that aren't stop signs or yield signs, things that aren't aeroplanes, but by God, they look like them. So you could imagine, for example, a stop sign that's reflected in a shiny surface on a windscreen. That's not a stop sign, it's a reflection of a stop sign. Can you manipulate parameters to make sure that things that potentially confuse the model because they are true negatives but could easily be classified as positives don't happen?
This is actually, like, we've had a very long discussion with Svet about how do we systematically create meaningful false positives. So this is something that we are actively looking at. But I think the reality is that some of the augmentations that we perform, even nowadays, create false positives, as in this case. And the interesting fact that we've analyzed in the use cases that we have is that they signify very specific model failure cases that would otherwise be very hard to detect. And in this case, it really is about the features around this boat that for some reason the detector thinks they look like an airplane, or when they're close to the horizon line next to the trees, so the branches like help to fold this. So this is something that we're looking at. There are a few strategies that we're trying out right now, but I think it's a bit of an early day to give a concrete example beyond this.
Okay, thank you.
Okay, do we have any other questions? I mean, I've got a couple that I could ask, but if you got any questions, put your hands up, and I'll catch you. And if not, then I'll just blunder on. And you can put your hand up at any time, and I'll take note of it. Yeah. So I wanted to ask you about measurement, and you think about improving along these axes, along the dimensions that you mentioned. As you get more domain specific, does that seems to become more of a problem? And actually, how are you thinking about specifying these measures, and as you get further along the line?
So if I'm understanding the question correctly, it's about how does the addition of extra dimensions in this impact the overall capability of being able to improve across all of the dimensions.
Mm.
Right, and I guess this is also highlighting that, you know, from my research career days, I can definitely tell you that training this system is kind of a whack-a-mole problem. You're fixing one thing and then you regress on another axis, and then you have to have, you know, 5 lines long like loss function in order to be able to perform like correctly across like different cases. And I think the first step in trying to solve this problem is to measure it. I think this is the tool that we're creating helps you identify how the system is behaving from, you know, the last 2-week sprint. Is it making any improvements, or have the improvement that you've made, you know, are they consistent with what you expect? And I think, you know, I think this is the first step. And then as you're building up, it's a matter of kind of balance and trying to really to figure out, and the addition of cases that you add to the training set can be reflective of what you found to be lacking in this axis. But yeah, I don't have an exact answer there. Yeah.
No, so I suppose that's where there was a kind of follow-up, which is you really focus just looking at dimension by dimension in some sense, and one thing that you might think is that there are lots of interesting combinations of these dimensions that you might want to consider. Yeah,
right. So yeah, I guess I should have clarified. This is actually what we're actively doing. We're not doing a single dimensional perturbations. We are searching in all of the possible combinations of dimensions. And this is why it is such a hard problem, because, you know, if you have, you know, 10 dimensions and 10 axes, then it's, you know, basically a 10 to the power of 10 possible variation. So you cannot feasibly add this to part of your training regime, but what you can do is kind of evaluate how you degrade. And there, from those samples, you can try to see what is the strength of the different, basically which dimension is contributing most to this performance in order to attribute it to one of those.
Okay. I don't. Well, maybe that was completely clear to everybody. It wasn't entirely clear to me from the talk. Yeah. Okay. Great. The other thing I wanted to ask about was, do you have ideas about how you might fit with current sorts of regulations in safety systems? Because these are rather, I mean, I have some familiarity there, and it seems like the introduction of this kind of approach, yeah, where in a sense you're using a modern delivery pipeline, and so these things are going to be changing. But if you like, the standard kind of safety critical software environment would typically say you should be turning off any learning, yeah. Once you've validated the system.
Yeah, I think that is the case, and I think this is a stark contrast with you know, some of the discussions that we have, especially in the medical domain. You know, their frustration really comes from the fact that once you know, create and train the system, you ship it in the product, and then you have no control over, you know, any sort of improvement and strategic methods of basically reevaluating the system. I think what we are trying to really build is a tool that allows people to observe, you know, have another way to view the performance of the system. So the way that you know, we want, I think it will be an interesting conversation to take it offline, but I think it's the way that we believe is that the tests that we perform should be aligned with what you know, we believe that, you know, from a government perspective need to happen, you know, in order to perform to basically create this adherence to the regulations by default. And I think once it's integrated into the standard MLOps pipeline and the way that generally the community thinks about developing these AI systems, I think this is the right goal where by default people are following these regulations.
Okay. Do we have any other questions? I mean, I have yet another final one. Alan, you seem to be kind of, maybe you're just typing. No, doesn't look like he's gonna. Okay, I had one final question to ask, which is really, I mean, so it's more of on an organizational basis. In terms of gathering new data, I mean, if you look at the thing at the very beginning, do you envisage having, how localized and distributed do you think that should be? Because I think if you have, if you like, a centralized data collection and kind of retraining of the model and so on, then you may be exposing yourself to more risk in the sense that you might be exposing yourself to some kind of class action or something like that. Do you, so how do you see the organization? Do you think that actually having something potentially quite localized or even personalized around this would be a good thing to do? I mean, I was talking to Ajitha this morning about how even within the same specialisms within the medical domain, the actual practices of the consultants vary very considerably from one to another. And so that actually the data that you get in these two contexts can be quite different.
Yeah, I think it's an interesting question whether or not in the data, I think it depends on whether or not the general data comes from a single entity, so from a single legal entity whose goal is aligned with the deployment of the system, or whether or not this is more of a overarching domain-specific way to perceive the problem that is, a natural human problem, let's call it. And so I think there is definitely, I doubt that hyper specialization to, on a person-by-person cases, I think it's going to lead to quite strong, basically overfitting to the observations. And I think as a group, so I think it's the fact that there is a strong change of domain as on a single individual basis. The variance I think is stronger than what we can observe as a group. So it would make sense that we should think about these processes on a group basis rather than on an individual basis.
Okay. No. Yeah, interesting. Did anybody have any more questions? I mean, this is getting a bit boring. I just keep asking questions, but I do have one final one. Final one. Is that okay, Daniel? If I ask?
No, sure. Go ahead. Yeah.
So you introduced this additional loop, yeah. I mean, it's a bit like the kind of second level learning, second level loop in Stafford Beer's stuff on cybernetics and so on. So it's about validation and deployment and monitoring, and the extent to which you reflect on that. So do you see in your development process that actually you should be gathering data on that loop and then subjecting it to not dissimilar kind of testing processes to the sort of thing that you're doing? I'm particularly thinking that might be where you would pick up bias, for example.
Yeah, I think the one of the comments that I want to stress is that I think right now what is happening, because of the speed of iterations of the system and the way that the systems are evaluated right now, when you have a data set that is being split and you evaluate on just part of it, or that is even split on more refined methods to kind of track particular axes that you're interested in, I think more or less right now, because of the speed of iterations, we are leaking information from the test set to the models through the humans that are performing the training of the models themselves. I think unavoidably we are overfitting to this static piece of data. I mean, the issues there are not only for the fact that it's static, that we're leaking information, and it becomes like very outdated. So it really needs a whole data pipeline on its own to maintain it. I think the way that we believe that it can be structured is that by looking at the whole operational domain of the validation set, you're undoubtedly enlarging the data support in which you expect the data to work on. So you get extra amount of kind of confidence when you deploy that you are more likely not to hit these boundaries of performance, or when you hit them, that you know the way that you degrade and because of the way that you search for these issues. And in reality, what's going to happen is that even though you are training on one part of your data set, you are going to perform basically the data generation step on the same data set that you've trained. However, you'll be evaluating on the domain of your validation set. So I think the data generation part and the kind of evaluation and robustness metrics, the clock or the circle that you see, are basically part of different data sets, but they work in conjunction to be able to deliver these improvements.
Okay, good. Okay, well, I think we're running out of time, and and thanks very much for an interesting talk. We'll one more round of applause, and thanks very much for an interesting seminar. Thank you. Thanks very much.
Yeah. Yes.
Okay. Bye now.